Today, we want to look at radian measure. This is just another way that we measure angles. The two major ways we measure angles are radians and degrees. So those are the ones that we want to learn to work with. The big idea here in radians is that we just need to learn how to convert radians to degrees. We just need to learn our common angles, that is quadrant angles 0, 90, 180, 270, and 360. And our common reference angles, 30, 45, and 60 in each of the four quadrants. We want to learn the radian measure of those angles. The reason that we are not going to like this is that all those angles are some fraction multiple of pi. And so we're dealing with fractions. And for the most part, students are numerical racists and they don't like fractions. The other thing is that in degrees, we have 360 degrees going all around the circle, and 360 is an awesome number. It's divisible by so many things. It's divisible by 2 and 3 and 5 and 10 and 12. And that means it's like 4 and 6. It's just crazy. It's just so divisible. Such a great number. But then we switch to radian measures and everything's like fractions. And so students are like, oh man, everything was nice whole numbers before, but now it's all fractions. And so it kind of upsets us. What we need is a point of connection between radians and degrees. Here are two good choices. Pi radians is 180 degrees. We're doing a lot of fraction multiples of pi, so we're going to do a lot of fraction multiples of 180 degrees. So it's whenever we see a pi, I want you to think that we can think of that as 180 degrees. So if I'm like, oh, pi over 4, you could think 180 over 4, that's 45 degrees. That is a helpful thing to start with. You also might want to start with a slight variation of this, and that's 2 pi radians is 360 degrees. This is the full circle approach. This pi equals 180, that's I'm going to see pi everywhere. I want to know what it means in degrees. The 2 pi equals 360 approach is to make sure that we connect this to a full circle. Here's why. When we have a unit circle, the circumference of the circle is 2 pi. If the radius is 1, so the circumference is 2 pi, and then going all the way around the circle, this is the angle, this is 0 degrees. I did not give myself a lot of space here. This angle all the way around is 2 pi radians going all the way around. Or you could just be like, oh, nope, 180 is pi. And so that just make sure that you have that connected in your mind with that angle there. That's pi radians, which is 180 degrees. Going all the way around, it's 2 pi, it's connected to the unit circle. The 2 pi is the circumference of the unit circle. So in a sense, we're connecting this distance with an angle, connecting some distance with some angle. Here's how we can practice learning our common angles in radians. Because this is one of the things that we want to do. We're going to learn one way to learn common angles in radians. One way that you can go about practicing this is to learn your common angles as fraction multiples of pi. So here are the three big ones. So I'm going to start actually with this one because it shows up most. 30 degrees is 180 over 6. So 30 times 6 is 180. So 30 degrees is pi over 6 radians. 45 degrees is 180 divided by 4. So 45 degrees is pi over 4 radians. And 60 degrees is pi over 3. Pi is 180. 180 divided by 3 is 60. And 90 degrees is pi over 2. Pi is 180 degrees, so 90 degrees is half of that, pi over 2. So we want to keep these 4. We want to remember these 4. Because going around the unit circle, our common angles are going to just count in these fractions going around the circle. So let's count our multiples by multiples of 30 from 0 to 360. So let's start off with 0 degrees is going to be 0 radians. That would mean be a weird system. That would be really weird. Oops. And I was thinking ahead too much. I could have changed that to, oh man. I'm glad I'm recording this so all these embarrassing mistakes just show up and get recorded on the internet. It's not like anybody watches this anyway. I did it again. So let's count by 30 degrees. I'm going to start 0 degrees and then 30 degrees, 60 degrees, 90 degrees, 120, 150, 180, 210, 240. So these are all in degrees. We'll just fill in as many as we can. So here are multiples of 30 going around the unit circle. We know that 30 degrees is pi over 6, and I'm just counting, so 0 radians. 30 degrees is pi over 6. 60 degrees is 2 pi over 6. 90 degrees is 3 pi over 6. 120 degrees is 4 pi over 6. 150 is 5 pi over 6. 180 is 6 pi over 6, and I'm just counting by fraction. 210 is 7 pi over 6. 240 is 8 pi over 6. And then it goes on from there. Now notice that some of these fractions can be simplified. 2 pi over 6 is the same as pi over 3 if we simplify it. So 2 pi over 6 is the same as pi over 3 if we simplify that fraction. And pi over 3 is 60 degrees. If I skip to the next 60 degrees, 120, 60 times 2 is 120. 4 pi over 6 is 2 pi over 3. The next 60 is 180. 6 pi over 6 is also just pi. So if you look at how we're counting things, if we count by 60s, we have pi over 3, 1 pi over 3, 2 pi over 3, 3 pi over 3. The next 60 is at 240. And that gives you 4 pi over 3 when we simplify it. So counting through by the 60s, it's just the simplified even multiples of 30. Still have 0 at the start. We can also notice that the 90 shows up because we got 3 pi over 6, and that's just pi over 2. When we simplify it. So if we count by 90-degree angles, the next 90 is at 180. Oops. 180 is just 2 times 90, so that would be 2 pi over 2. And at 180, that's where we get to our base case, where 180 degrees is pi radians. So the 180 is 6 pi over 6 because it's 6 times 30, 3 pi over 3 because it's 3 times 60, 2 pi over 2 because it's 2 times 90, or just 1 pi because it's 180 degrees. If I went one further, I know I should have gone one further. At 270 degrees, we are at 9 pi over 6. Which is 3 pi over 2. So it's also 270 is also 390. So we could write that as 3 pi over 2 down here in the 90 row. Any questions? And then we have to keep going. So what I want to emphasize today is that we want to be able to count by fractions. I know some of you might be like, oh, but I don't like fractions. And it's just like, well, fractions are a thing, so we have to learn to deal. I'm not saying you have to like fractions, but you do have to tolerate fractions. Any questions? Notice that the ones that we missed here, since I started as my base case of multiples of 30, multiples of 30 are also multiples of 60, are also multiples of 90, and are also multiples of 180. And we just broke it down into fractions. And I have a row for the pi over 6s, a row for the pi over 3s, and a row for the pi over 2s. No, and a row for the pi. So when we're learning common angles in radians, I encourage you to learn them as these fraction multiples by just counting the fraction multiples. Now you might notice that we did not, since we were going with multiples of pi over 6, we did not end up with the multiples of pi over 4. So let's count around the unit circle in multiples of 45 to get that pi over 4. Separate this one. So if I start off with 0 degrees, that's 0 radians. Hey, I finally successfully did that. The next multiple of 45, so we go 45 degrees, that'll be pi over 4 radians. The next multiple of 45 is 90 degrees, and that's going to be 2 pi over 4, because I'm just counting. And then 135 degrees is 3 pi over 4. This was a popular choice, by the way, in the discussion. 180 with the pi over 4s. 180 degrees is 4 pi over 4. 225 is 5 pi over 4. Notice we're just counting multiples of pi over 4. No pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4 is at 270. 315 is 7 pi over 4. And 360 is 8 pi over 4. Notice that in the multiples of 45, we also land at the multiples of 90. This is because 360 is an awesome number. So notice that if we simplify our 2 pi over 4 to pi over 2, that's a 90-degree angle. The next one I can simplify is 4 pi over 4. That's going to be 2 pi over 2 if I'm counting by 90s, because 180 is 2 90s. 270, just like before, is 3 90s, so 3 pi over 2. And 360 is 4 90s, 4 pi over 2. But we would simplify 2 pi over 2 to be pi, and that's at 180 degrees. And if we count the multiples of 180, 2 pi is 360 degrees. This is, admittedly, a weird way to lay things out. All of our instincts should be to draw a big unit circle and just go around the unit circle and look at the multiples. But I like to look at things from a different view. I want to look at things going across, because that's one of the things that we want to use radians for. Trigonometric functions have graphs that are going to be periodic. They're going to go up and down and up and down. And so they're very good at modeling things that are periodic. But using degrees as our time input is really inefficient. It makes things look really weird. So we use radians as our real number inputs. So what your job is by next week to have all of the common angles in radians and degrees. So going all the way around the circle, 0, 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and 360, all in multiples of pi. Look at your pi over 6s, your pi over 3s, your pi over 2s, and your pi over 4s. Any questions? The other thing that we're getting out of this is we're learning how to count with fractions, which is not a skill that many of us are walking around with typically. So the other thing that I want to look at today is counting with fractions. Less of a trig thing and more of a fundamental skill. Fractions are going to show up at our radian measures of common angles are going to show up as multiples of pi. And we're going to have a lot of fraction multiples of pi. So we should be familiar with how fractions work and counting with fractions. Because I just asked you to do this. Count by pi over 6s, count by pi over 4s, count by pi over 3, count by pi over 2. Count around the circle in those multiples. And then draw it as you're doing that as well. So let's just talk in general about counting with fractions. Let's suppose that I'm going to count with 1/3. So this is what I want to count with, 1/3. So let's suppose I have, I'm just going to start off with 0. That's 0/3. And then I'm just going to count 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, 7/3, 8/3, 9/3, 10/3, 11/3, 12/3. Notice that we're just counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, I struggle there because every time I count to 12, the only way I can do it, and none of you are old enough to remember this, but the only way I can count to 12 in my mind is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the only way it comes out in my mind. I don't know, if I count to 10, it comes out normal. But if I know I'm counting to 12, that's the only way it comes out. I know none of you know where that comes from, which is okay. And I can, the picture in my mind is like a pinball running around like some crazy pinball machine. And just like the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it's very, very funky and disco-esque. So these are not how we list most of these numbers. Notice that 3 over 3, we usually simplify that. The common name for 3 over 3 is 1. Usually we refer to 3 over 3 as 1. Usually we'll refer to 6 over 3 as 2, and 9 over 3 as 3, and 12 over 3 as 4. Because when we get to, once we filled out 3/3, then we have one whole thing. Then when we have 6/3, that's 2 whole things. In between, we can convert our improper fractions to mixed numbers. So 4/3, 3 of the thirds is 1, and 1 of the thirds is a third. 5/3 is a 1 and 2 more thirds. 7/3 is 2 and a third. 8/3 is 2 and 2/3. 9/3 is 3, so 10/3 is 3 and 1 more third. And 11/3 is 3 and 2/3 before we get to 12/3, which is 4. Notice that if we can read this list strangely if we want. This is like a 1, and this is 1 and a third, and then this is 1 and 2/3. We could call 6/3 as 1 and 3/3, and 7/3 is 1 and 4/3, because we're still just counting. And then 8/3 is 1 and 5/3. 3 is 1 and 6/3. Now, these are not how we commonly list these fractions. But it means the same thing. One thing that's important to note is that when I write the fraction 1 and 2/3, we are literally saying 1 plus 2/3. We just don't write the plus because we've all agreed that we don't need to write the plus. We'll just say the word and we'll just smash the two together. And then some overly pedantic jerk will be like, don't we use juxtaposition for multiplication, like xy means x times y? And then the rest of us were like, don't be so pedantic. Okay, it's going to cause confusion later. And what do we have now in the 21st century? People what don't like fractions. So that guy's like, see, you should have listened to me. But we're just counting with things, and we're just counting with fractions. And sometimes we simplify those fractions. These are the common names for things. This is a weird set of names. 1 and 3/3, we should call that 2. And then 1 and 4/3 is 2 and a third. 1 and 5/3 is 2 and 2/3. 1 and 6/3 is 2 and 3/3. 1 and 7/3 will be 2 and 4/3. And now we're getting into some weird names for things again. Here's the reason that I look at these weirdo fractions. I look at these weirdo fractions because we know that to get from the improper fraction to the mixed number, we use division. So if we want to go from an improper fraction to a mixed number, if we want to go from an improper fraction to a mixed number, the technique is to use division. So to go from an improper fraction to a mixed number, we use division, long division if we're going to do it by hand. So let's pick 7/3. That's fine. 7/3 will do. So I'm going to pick sufficiently small numbers. So if we have 7/3, and we want to write it as a mixed number, we use division. 3 goes into 7. I don't know what the incantation you were taught when you were taught this division algorithm. I'm just going to use the words that I was taught. I was taught to say 3 goes into 7 twice. So this is the words that are running through my head. I come up with this 2 because I say to myself, 3 goes into 7 twice. I wasn't told why this was. I was also told to look for the biggest multiple of 3 that's less than 7. And I was told it had to be 2 because 6 is less than 7 and 9 is too much. So it's 2 and then I multiply. 2 times 3 is 6. And then I subtract. 7 minus 6 is 1. And so my whole number part is 2. My remainder is 1. That's going to be the numerator of my fraction. And then the third is the denominator of the fraction. Any questions? So some of you may have learned a different algorithm for this division thing. And some of you may not have. Some of you may have just been told to memorize things. I'm going to create a discussion, and I want you to respond in the discussion a description of what you were taught, how you were taught to do division. Because it's always interesting to see what students have been taught. Were you given the same incantation that I was, even though I'm like twice your age? Or were you taught something new and interesting? Here's what I really wanted to talk about. I was told to use these words, and I can't get them out of my head. It's like counting to 12. I can't get the 3 goes into 7 twice out of my head. But I have been thinking about it since. So I've only been thinking about it for, like over 40 years. It's like, why do I keep saying that? And then as an adult, I realized because I was programmed to say that as a child. I'm like, oh, they treated me like some kind of machine. Then I started wondering if I was a machine. I'm pretty sure that I'm not. Pretty sure. So 3 goes into 7 twice. What this means is that I'm asking how many times can we subtract 3 from 7 without going negative? Some of you are like, oh, dude, that's obvious. Like, oh, it wasn't obvious to me for a very long portion of my life. For a very long portion of my mathematical life, it was not obvious to me that this statement means how many times can we subtract 3 from 7 without going negative? So how many times can we subtract 3 from 7 without going negative? I wasn't told that that's what it means. Mostly because I wasn't given instruction on what the operations mean. So the way that I think about operations now is that multiplication is repeated addition and division is repeated subtraction. That's the way I think about multiplication and division now. As it relates, I think about those operations as they relate to the base operation of addition and its inverse, subtraction. So this says, how many times can we subtract 3 from 7 without going negative? And that's 2 times. So this minus 6 is literally subtracting 3 from 7 twice. That's what that negative 6 is about. So the answer is, so when I ask the question, how many times can I subtract 3 from 7 without going negative? I come up with the answer twice. And here we are. Subtracting 3 Or here we are subtracting 3 from 7 twice, subtracting 2 3s from the 7. And then there's 1 left over, so we call this 2 1/3. It lands right here on the same as the 7/3. Great. Here's why I think we really missed the boat when we were just told, no, it's got to be 2. 3 goes into 7 twice. When it stops there, then it requires us to have this precision, and it doesn't require us to understand what's going on in our subtraction. So let's deliberately get this wrong and see that everything will work out just fine. Let's suppose that we say, okay, I'm going to take 3 and divide it into 7. We got to subtract 3 from 7. How many times can we subtract 3 from 7? Technically, as many times as we want. Let's suppose that we get it wrong. Let's deliberately get this wrong. Let's suppose that instead of subtracting 3 from 7 twice, we're gonna subtract 3 from 7 one time. 1 times 3 is 3. 7 minus 3 is 4. So we'd be like, all 7/3 is 1 4/3. And then we'd be like, oh, hang on. I could have subtracted another 3 from the 7 because I've got this 1/3 here. Notice that 2 1/3 is the same as 1 4/3. So we're like, oh, hang on. I've got too much. I have another whole number in this 4/3. So I could subtract another 3 from the 7. Because I'm left with 4, that tells me we could have subtracted another 3 from the 7. Not a notre. There we go. We could have subtracted another 3 from the 7 because we ended up with 4, and there's another 3 in the 4. But 1 4/3, we can see way up here that 1 4/3 is the same as 2 1/3. Let's suppose I go through and I get this problem. I'm going to get this problem wrong yet again. Let's suppose here we were being overly cautious. I'm only going to subtract 3 from 7 one time, just once. Oh, I could have done it again. Let's be overly aggressive. Let's subtract 3 from 7 too many times. Let's suppose that we say, I'm going to subtract 3 from 7. How many times can we subtract 3 from 7? If we ignore the without going negative part, as many times as we want. I'm going to subtract 3 from 7 3 times. 3 times 3 is 9. 7 minus 9 is -2. So instead of 1 4/3 or 2 1/3, I have 3 2/3. So I go, oh, dang, I took too many 3s away. So whoops, we subtracted too many 3s. But 3 minus 2/3 is equal to 2 1/3. This is the great thing about the long division process. If we remember what's actually happening in the long division process. No, don't just break it down into the 4 things. Divide, multiply, subtract, bring down, divide, multiply, subtract, bring down. If we go past that and we just take a look at what we're trying to accomplish with this algorithm and this weird way of writing things, we don't force ourselves into a corner by having to get this number correct and then redoing the whole thing if we get it wrong. If we understand what the process is trying to tell us, then we can correct when we don't go far enough, or we can correct when we go too far, if we understand the process, instead of just program ourselves with the one way. That make sense? This is what this is what math education in the 21st century is trying to accomplish. The fact is, we don't need to be good at this by hand. It's not about being fast and efficient to do this, because if you want speed and accuracy, we have an answer for that. This thing is always going to be faster than what you can do by hand. If you're writing things down, you are automatically slower, because by the time you finish writing things down, calculator's like, oh, hey, I got the answer there if you want it. You know, I'm just if you want speed, think calculator. You know what I mean? And the reason I phrase it this way is that a lot of people complain about how math is being taught to people, how math is being taught to other people. And I'm saying, isn't it faster just to do it the other way? Well, yeah, speed's not the point anymore. Maybe speed was the point when you were in school 30 years ago, but it's not anymore. Now understanding is the key. Most of the people that I know outside of school don't understand math. I know some people that took calculus and they don't understand math. Like math, calculations. Anyway, I know that this went off on a little bit of a counting with fractions tangent, but we want to have our fractions in play because going around the unit circle, we're trying to learn our common angles in radians, and radian common angles are going to be fraction multiples of pi. So we got to know how to count in fractions. That's going to do it for today. It's Wednesday, so everybody have a nice weekend. I'll see y'all on Monday, and thanks for playing.